All right, let's dive in. Today we're going to pull back the curtain on one of the most fundamental tools in all of machine learning, linear regression. I know it sounds super technical, but trust me, it's a surprisingly simple idea that lets us predict the future. Everything from house prices to company sales. Let's see how it all works.
So think about this for a second. How can we predict the price of a house? You've got all these different factors, right? The size, the location, how many bedrooms. You'd think it's this crazy complex problem. But the core idea we're exploring today is that we can find a surprisingly simple pattern in all that messy data.
So here's what we're going to cover. First, we'll tackle the prediction problem itself. Then we'll look at the simple, straight-line solution. After that, we'll get into how a model actually learns, see it in action in the real world, and finally, go over some super important rules of the road for using this tool the right way.
All right, first things first, let's talk about the prediction problem. At its heart, this is all about forecasting the future. Businesses have to predict sales, scientists need to model climate change, and all of these huge challenges, they all come down to one thing: predicting a number. And that's exactly the kind of problem linear regression was born to solve.
Okay, so what is linear regression, really? Well, it's what we call a supervised learning algorithm. Now, supervised just means we teach it by showing it examples where we already know the right answer. Think of it like giving it a stack of flashcards. We show it a bunch of houses with all their features and, this is the key, their actual sale prices. The algorithm studies these examples, learns the relationship, and then it can predict a price for a brand new house it's never seen before.
Okay, so here's where the magic happens, and it's simpler than you might think. We're calling this the straight-line solution. At its very core, linear regression works by finding a single straight line that best fits the data, that best describes the relationship between what we know, like a house's size, and what we want to predict, like its price.
And this is the secret sauce. This simple little equation is the engine that drives the whole thing. Here, y is the price we're trying to guess, and x is something we know, like the square footage. The model's entire mission, its only job, is to figure out the perfect values for b0 and b1 to make the most accurate predictions possible. And this is where it gets really cool. Check this out. Y is our guess, our prediction. X is our input, say the size of the house. Now b1 is the slope. This is the fun part. It tells you exactly how much the price goes up for every single extra square foot. And b0, that's the intercept. Just think of it as the base price for a house, even if it had 0 square feet. It's that simple, and you can explain every single piece of it.
But wait, you're probably thinking a house is way more than just its size, and you're totally right. But the beautiful thing about this model is how easily it scales up. When we want to add more inputs, like the number of bedrooms or the age of the house, it just becomes multiple linear regression. We just keep adding more ingredients to our recipe. Easy. Okay, so that's the what. But how does the model actually find those perfect numbers for the intercept and all those slopes? Well, that brings us to the really fascinating part: how a model actually learns from data.
It all starts by measuring its own mistakes. The model makes a guess on a house it's seen before, then it looks at the actual price. That gap between its guess and reality, that's the error. It does this for every single house in the training data, and then crunches them all down into a single number that represents its total error. We often call this the mean squared error, or MSE. And the model's whole job, its only job, is to tweak itself over and over until that error score is as tiny as it can possibly get.
And the way it minimizes that error is through a clever process called gradient descent. Imagine this. It starts by just drawing a random line through the data. Then it measures how bad that line is. That's the total error, or cost. Now here's the smart part. It figures out which direction it needs to move the line to make the error smaller, faster. It then just nudges the line a tiny bit in that direction, and then it does the whole thing again, and again, and again, taking these little steps until it finally settles on the one line that fits the data with the lowest possible error.
All right, enough with the theory. Let's talk about where this stuff actually gets used in the real world. Let's put this tool to work.
And the answer is, well, pretty much everywhere. I mean, seriously. Real estate, obviously, for house prices. Finance uses it for trying to forecast stock performance. Marketers use it to figure out how their ad budgets are affecting sales. It's even used in healthcare to predict medical costs, and in retail to forecast exactly how much stuff they need to have on the shelves. It is incredibly versatile.
So let's make this super concrete with a sample house price equation. This is where we get to see not just a prediction, but a full-blown explanation.
And this is why linear regression is so awesome. Look at this. A trained model might say a house starts with a base price of $30,000. Then, for every extra square foot of size, you add $120 to the price. For every bedroom you add, you tack on another $15,000. And for every year the house gets older, it knocks $2,000 off the price. So you see, it doesn't just spit out a number, it tells you why the number is what it is. It's completely transparent.
But, like any powerful tool, you can't just swing it around blindly. You have to use it correctly. And that brings us to the rules of the road. There are a few key things we need to be aware of to make sure our model is actually reliable.
First, the relationship actually has to be linear. A straight line needs to make sense for the data. Second, the data points should be independent. One house's price shouldn't directly be influencing another's. And finally, you have to avoid something called multicollinearity, which is just a fancy way of saying your inputs shouldn't be telling you the same thing. For instance, you wouldn't want to include both the size in square feet and the size in square meters. It's redundant and it can really confuse the model.
Another huge thing is finding that perfect balance. On one side, you have underfitting. That's where your model is just too simple and it completely misses the real pattern. But on the other side, you have a major trap called overfitting. This is where your model gets too complex. It starts to memorize the training data, including all the random noise and quirks. So it gets amazing at predicting the houses it's already seen, but it completely falls apart when you show it a new one. So how do we fight that? The most common weapon against overfitting is a technique called regularization. You can basically think of it as adding a simplicity penalty while the model is training. It discourages the model from putting too much weight on any single feature, forcing it to build a more general, more robust understanding of the data. It learns the real trend, not the noise.
All right, so let's tie this all together. Here's your linear regression toolkit in a nutshell. It predicts continuous numbers, things like prices, sales, or scores. It works by fitting the best possible straight line to the data. It learns by systematically making its own mistakes smaller and smaller. It's super explainable, which is a huge deal in the real world, and honestly, it's a powerful and versatile foundation for just about everything else in machine learning.
So I'll leave you with this. Now that you've seen how a simple straight line can be used to predict something as complicated as the future price of a house, what other big, messy, complex problems out there are just waiting for a simple, elegant idea to come along and solve them?